Hello everyone, Chris Miller here. Before you watch the video from my class today, I need to talk directly to those of you who are not in my class and watch my instructional videos on YouTube. For those of you who do not know, I'm a professor in the Department of Statistics at the University of Nebraska-Lincoln. Administrators at my university have recommended the elimination of my department. All faculty, including me, will lose their jobs. I will not be able to post an instructional content like this to my YouTube channel anymore. And also, most students in the department will not be able to complete their degree programs here. It may seem strange or odd to you that a university would actually eliminate a Department of Statistics given the growing importance of statistics, data, and data science in general for the world. And we all feel exactly the same here. There is still a chance, though, that administrators will change their recommendation. If you like the content that I make available on YouTube, and if you think that statistics is important, please let my administrators know it. In the content description for this video, I've included information about how to send them a letter or just a small comment. With your help, I hope we can save the Department of Statistics, and if we are successful, I promise to continue posting these instructional videos. Thank you very much. Okay, time's 12:30, so why don't we begin? So today we will continue in principal component analysis. We'll also talk a little bit about project number 1. Are there any questions?
Yeah. Is the document for project number 1 somewhere? I was looking around and couldn't find it.
It should be on the graded webpage of the course website. If you still can't find it, let me know.
Oh,
yeah.
Obviously,
that would be bad if it wasn't out there.
Yeah.
I would feel really bad. So again, remember, save our stats. Have your voice heard. If you haven't already done that, there's a website where you can submit some feedback about the elimination of the Department of Statistics. This was in at least the Omaha newspaper yesterday. The affected departments requested that the budget reduction process stop because the university is not following the rules. And unfortunately, the Chancellor's office told us, no, we are following the rules. It's easy to see that they're not, but they say they are. Also, we talked about the Board of Regents meeting. That's going to be tomorrow at UNMC. They often live stream them. I can't find a link yet, but if you're interested, you can watch it. There's going to be a number of people from the university going up there to talk about the issues with the budget reduction process, including there will be 2 faculty from my department that will be up there, where we will talk about the data. Faulty analyses, faulty conclusions. That's what they're using to try to eliminate the Department of Statistics and all the other departments. Okay. So we were talking about principal component analysis. This is one of my more favorite topics in this course. The basic idea is this. You have a whole bunch of variables. So many, it's kind of hard to make sense of them all. Of course, these variables are going to be related to each other in some way, meaning that they're going to be correlated. What principal component analysis tries to do is take these original variables and transform them into a smaller number of variables that are more manageable to work with and also are uncorrelated to one another, meaning that they represent distinct pieces of information about your data. Okay? So, to talk more about the math behind this, suppose we have a random variable x. It's p by 1, meaning we have p variables represented by x. It comes from some population that has some distribution. We don't know what it is, but we can represent the expected value of x as mu, so the mean. So that's p by 1. We also have a covariance matrix, sigma, which represents the variance amongst the variables and the relationships amongst the variables, the covariances. Okay. So these new variables that we are going to form, they have a special name. It's called principal component. That's why we have principal component analysis, the whole name. And there's going to be a number of these variables. The very first one that we're going to form is going to be called y1, y sub 1. And all it is essentially a linear combination of your original variables. Here's how the linear combination is found. So we take x1 here, which is the first of our original variables, subtract off its mean, then we multiply it by a constant. Let's call it a11. So what we're basically doing is we're centering this x1 to be we're making the center of this x1 to be 0. In other words, well, what's the mean? What's the expected value of x1 minus mu1? 0. So we're mean centering, you could say. That's not a good way to put it. How about we just say the center of it is now 0? Okay. This is often done in some other statistical procedures too. We're trying to take the mean out of it. Then we go to the second variable. We do exactly the same thing with it. Multiply by a constant, called a sub 21. We do that through all p variables to form this linear combination. We can represent this in a matrix algebra form by taking the x vector, subtract off mu, take a time of vector, let's call it a1. And we transpose it to make sure all the matrix algebra works. Now, of course, the mean is unknown. We'll talk about how to get around that problem shortly, okay? It's a simple thing. But this is how we find this first new variable, this first principal component. Now, the question is, what do we use for these coefficients on this linear combination? What do we use for these a's? And this a is chosen so that the variance of this linear combination is as large as possible. Now, why do we want to do that? I was kind of getting at this last time, and that is, in statistics, we often equate understanding variability to understanding information about your data. So the more variability that y1 accounts for, the more information it's going to account for in the data. That's why we're doing this. Also, we're going to say that these a vectors, or this a1 vector, has a length of 1. Okay? Now, what's cool is this. Well, what is this maximum possible value? It just so happens that one can prove, a mathematical proof, that this maximum is the largest eigenvalue of that covariance matrix. That's why we talked about eigenvalues and eigenvectors. It's the maximum possible value of the covariance matrix. I'm sorry, it's the maximum eigenvalue of that covariance matrix. Let's call that lambda 1. And the corresponding eigenvector that has a length of 1, that's what we use for A1. Kind of interesting. Now, I'm sure all of you are saying, Chris, do the mathematical proof for me. Sorry, I'm not going to do that. I'm going to let you down. Why? Well, first of all, if you do want to see it, it's in this standard textbook for multivariate data analysis. It's not my favorite book out there, but it is probably the most often used. Now, to give you perspective about what you need to have as a background to understand the proof, I first saw the proof during my second year of grad school. So it would have been the second year of my master's program. And I did my PhD after that. Second year of my master's program, I saw the proof there. And it does require a much higher level of understanding of matrix algebra than what we're doing here. So that's why I don't think it's worthwhile for us to go through all that background material before we can actually get to the actual proof. So you'll just have to accept that this is the result. Okay. So I've already said this part here on page 5 about why do we want to maximize this variance? The key thing that you need to get out of this is that we are maximizing the variance because that's going to maximize the amount of information that we know about our data. How do we do that? We use the the eigenvector corresponding to the first eigenvalue of your covariance matrix. So we can find other new variables too. So let's talk about now the second principal component. We're going to call that y2, and you can see it's formed in exactly the same manner. But now that vector a2 that's forming that linear combination corresponds to the eigenvector of the second largest eigenvalue from the covariance matrix. And so what this is doing is it's saying, and it's also this, remember how eigenvectors are orthogonal to one another? Okay? What that actually ends up meaning for us is y1 is independent of y2, if we think of them as random variables. So they represent distinct sets of information about your data. You can keep on going to get a third principal component, fourth principal component, doing exactly the same process. Now, since these eigenvectors are actually orthogonal to one another, basically what this allows us to do is use an orthogonal axis system for these new variables that we're forming, principal components. Well, what do I mean by that? Well, I kind of foreshadowed this in the data distributions and correlation section. Okay, you remember that plot? So what we have here is a contour plot for a multivariate normal. We have the eigenvectors corresponding to the covariance matrix. They're pointing in certain directions corresponding to the major and minor axis of the ellipse that forms the contours. And what we see here is what we normally think of as an orthogonal x-y axis. And I said at the time, imagine if we could, let's say instead, form a new set of axes that looks something like this. So you can tilt your head. Now you have a new set of orthogonal, or perpendicular, since it's two-dimensional, a new set of orthogonal axes. Why would we want to do that? I'm sorry, this was the actual plot that we did that for. Okay? Why would we want to do that? Notice this new y1 axis. I purposely used y1, knowing that we were going to talk about this in principal component analysis. Look at this y1 axis. In this particular multivariate normal, we had it such that, let me actually see if I can remove this. So what I have here are these blue dots is, let's say that's where the data would fall, because in this particular case, this was a multivariate normal that had, we had high correlation between x1 and x2. That's where all the data points would fall. Notice there's not much variability in the y2 direction. All the variability is in the y1 direction. So if we could draw a new coordinate axis system, basically what this is telling us, all we would need is y1, and we would be sacrificing very little information about our data if we just threw away y2. That's what principal component analysis does. Okay? Any questions? I know that is an abstract concept, but that's what's happening here. So here's a question for you. Well, how many principal components do you think you can have in the end? How many eigenvalues can you have of your covariance matrix? Yeah, so you could have, in a general sense, p. So you could actually have up to p principal components. Would you want to use p principal components? No, because you're not gaining anything from that. Just use your original data then. What you're hoping for is that, let's say you choose d principal components, and that d is less than your number of original variables, p. It's less than enough that it's going to be beneficial. It will allow you to be able to make more sense out of your data since you're working with a smaller number of variables.
So then we have to be able to figure out, how do I choose D, the number of principal components that I will want to actually use in the end? And that's where this concept of total variance comes about. And basically all it is here's your covariance matrix. Let's just sum up all the variances. So everything that's on the diagonal. So in other words, we're taking the trace of that matrix. Again, in statistics, we often equate variability, understanding variability, with the information that we have in our data. So what we want to do then is choose, excuse me. Yeah. So the total information that we have in our data then is essentially what I just called the total variance. The total amount of information we have in our data is essentially the total variance. It's a little bit more complicated than that, but go with me. And so what we like to be able to do is this. Remember how the variance of y1 is equal to that largest eigenvalue, the first eigenvalue. What we hope is that if I look at the ratio of y1 over the sum of all the lambdas, you might be thinking, well, wait a second, why can I do that? It's because the trace, I have it right here actually. The trace of a matrix happens to be the sum of the eigenvalues. That was something we learned in the matrix algebra section. Why that occurs is not important for us, but just realize that's what it is. What we're hoping is that then that this proportion that we're going to get, so this is, I have to be very careful here, I equal 1 to p. This is a summation symbol, not a covariance matrix. Lambda 1, or the sum of all the eigenvalues, we hope that proportion is as great as possible. So let's say that that proportion is 0.95. What that says is that first eigenvalue accounts for 95% of the variability, of the total variability in the data. In other words, 95% of the total information available in our data can be accounted for by only using y1. If we had something like that, we would be extremely happy. Instead, what might happen is maybe this ratio is 0.4. So that first eigenvalue, that first principal component is only accounting for 40% of the information in your data. Think of it from a data analysis point of view. Would you be comfortable with just using y1 for a data analysis if only 40% of the information about your entire data is in it? No. So then you go to your second eigenvalue, or the second principal component. Okay? And now you look at that corresponding ratio. If that ratio is high enough, you will say, okay, yeah, let's just use two principal components. That gives me all the information I need about my data, or most of it. So you might be left in a situation of, let's say now you're at, 0.75. And then you're going to have to make a decision. Is it worth giving up 25% of the information in my data? It may or may not be. So there's going to be like a little bit of I'm not going to give you one particular percentage to look at. It's kind of fuzzy. My general rule of thumb is I want to try to get at least 80%. But there are times where I dip down. And there are other times where it's like, okay, if I use one more principal component, I can get over 90. I'll do it. So you'll see some examples of that coming up. So the key is, how do I choose the number of principal components? I look at that ratio. That helps guide me. And let's see here. Yeah, we can go. I had an idea of how different to approach that. I don't want to do that idea now. Just note that there was a small little thing that I did remove. It's not a big deal, but if you want, you can remove it. So basically, how do we determine the number of principal components then? We look to see, we want to have enough principal components such that 100 times, this is just to be general, gamma percent of the variability is accounted for. So in other words, find the smallest d such that this ratio is greater than gamma. So I might say, okay, maybe gamma is 0.8. I'm going to use as many principal components such that I'm above 0.8 for this ratio. Maybe it might be 2. Maybe it might be 3. Maybe it might be 4 principal components. Another way that people do is use what's called a scree plot. And this is what it looks like. So on your y-axis, you have the lambdas. And again, remember, these are the variances of your principal components. On the x-axis, you just simply have numbers corresponding. Is this going to be for the lambda 1, lambda 2, and lambda 3? And notice I do not have a numerical scale on this y-axis here because I'm just trying to be general. But what we see here is eventually once you get to 3 principal components, things start to level off. Yeah, this is an error. That should be a 3. Make sure you make that change there. That should be a 3. Notice how things start getting level off. When you see something like that, that should say to you, okay, I could keep on using more and more principal components, but the amount of information I'm gaining is not that much. It's almost like if you've heard like the law of diminishing returns. Eventually you get to a point where if you keep on adding more of these y's, it's not really worthwhile. So in a scree plot, which that's what this is, you simply look at a plot of the eigenvalues. And once you see that leveling off, that tells you when to stop in terms of what D should be. Yes? Yeah.
You have written that lambda j is variance of our y of j's. But wasn't the case that lambda j's were the eigenvalues of that covariance matrix?
They are. Yeah, let's go back. I know this, especially since I didn't go through a mathematical proof, that might take a little bit of time to sink in. So this variance here is the variance of y1. They're equivalent. These two expressions, they're equal. Okay. That variance, or that maximum variance occurs when you use that eigenvector in that linear combination. And because you're using an eigenvector, what ends up happening is that variance happens to be lambda.
My question was that
Sorry?
when we will be doing this principal component analysis, so we don't know y1 yet, but we know lambda 1, the eigenvalue.
Yeah.
So directly take that values and put it in a scree plot.
So yeah, you can calculate obviously the eigenvalues, eigenvectors from the covariance matrix.
Yeah.
You put them in the scree plot. That tells you then, if you use that technique, tells you how many principal components to use, how many y's. Okay, we will have an example very shortly. Thank you for the question. So, in the expression that we have for y1, remember how I pointed out that mu was in there? The problem is, of course, mu is a population quantity. You're never going to know exactly what it is. So what do? Well, you estimate it. Okay? Also, remember, sigma is playing a very important role, the covariance matrix. But we don't ever know exactly what that is. It's a population quantity. So what do? You estimate it. So you find the eigenvalues, the eigenvector of the estimated covariance matrix. And then that's how you proceed when you're actually using data for principal component analysis. So we saw in the data distributions and correlation section how we do that estimation. And so what we actually end up that we can actually calculate is basically something that looks like this. So notice I put a hat on top of mu. I'm going to put a hat on top of A because this is going to be calculated from the estimated covariance matrix. And so in the end, we will get y hat sub j for the jth principal component. Okay, let's actually jump ahead and talk about doing some data analysis. or working with data. We don't really get to the analysis part just yet. Okay. So I'm going to use the goblet data that I briefly introduced earlier in the course. It's also in the practice problems for this course. Here's what the goblet data, or here's what a goblet looks like corresponding to the variables that we're measuring. Again, the basic idea behind this is that we have an archaeological site, and we have these goblets that are being found. They're being dug up. And the researchers, archaeologists, want to eventually develop some way to classify these goblets so that goblets are similar to one another in each of these classifications. And so they take these measurements to help them do that. And one thing, though, is that they want goblets to have the same shape, to always be classified together, even if they're a different size. So, the size of the goblet may be this big, and another goblet may be this big, but as long as it's the same shape, meaning, let's say how much the opening of the goblet is relative to the size of the goblet, as long as that is the same, we want to be able to classify them together. So, where I got the data from, they suggested, how about we adjust the data by dividing each of the variables by the height variable. So essentially, we're not going to use x3 directly in our analysis anymore, but what we're going to use instead, x1 divided by x3, x2 divided by x3, and so on. Okay, so let's go ahead and look at how we can read in the data. So you can download goblet.csv from my website. So I'm going to read in the data. And let's just do a head on it just to make sure it looks right. Yes, it does. I meant to do this. I think these are centimeters, these measurements, in terms of their lengths. And then to do the transformation, what I decided to do was this. I created a new data frame where the first variable is going to be what was originally the goblet variable, which just gives me a number. It's an ID number, that's all. Sorry. That happens very rarely to me. I apologize. That won't happen again. And then I'm going to create another variable called W1, where it's going to be x1 divided by x3. I do that for the other variables as well. We take a look at what the new data frame looks like. If you want, you can verify that it worked. It did. Okay. Now that we got this data set, we're going to apply some stuff that we learned about in the last section. Once you get the data, let's plot it. So here is a plot of the data. This is a stars plot. So we can see, for example, the black portion of the stars plot represents W1. I've also included labels corresponding to each goblet. Goblet 1 through 25. So what goblets here do you think stand out from the rest? I mean, we have some stars that look quite different from the rest. Just shout out some names, some numbers corresponding to things that look maybe similar. 25 and 20, I agree. Okay. Well, how about some other ones?
4 and 5.
Yeah, 4 and 5. At least those are the ones that really stuck out to me initially. Look at how 17 and 18, and then they're a little bit smaller, but they're kind of like that. But then we also have a number of these really small stars as well. So what this is telling me from this initial look is maybe there is some way that I can classify these goblets that are similar to one another. Also, what we can do is a parallel coordinates plot. And so I have W1, W2, W4, W5, W6 here. Well, I didn't need to do this. I did here. Let me actually go over to R because I don't think we've necessarily talked about this function before, but you might have seen it in another class. Let me go ahead and run that code. Okay. I wasn't for sure how I could get color on the parallel coordinates plot and to have it meaningful in some way. And so from looking at the diagram of the goblets, of a goblet, notice how X5 kind of connects everything. So I thought, how about we put some color on the plot corresponding to, is a particular goblet less than the median of W5 or more than the median? There's not a right or wrong way to do this. I was playing around with it and I thought, okay, well, why don't we try that? So how can I do that? I can use in R what's called an if-else function. This works essentially just like the if function in a spreadsheet software package. So if I say if else, I'm going to test, is the W5 variable less than or equal to the median? If it is, assign a color of red. If it's not, assign a color of blue. So let me go ahead and run that just so that you can see. And there we see a bunch of reds and blues. Then I can use the parcoord function, where what I'm going to do is remove the very first variable from that data set. I could have plotted it. It's not that big of a deal, but it's just the ID number. And so to do that, I say a -1 to say remove column 1. The colors that are going to be plotted are the reds and blues, and put a nice little title on the plot. And this is what we get. Okay. Anything that stands out to you here? So, what do we look for with parallel coordinates plot? We can look for outliers. We can look for trends across the variables. Is there anything that stands out? How about outliers? Let me go over to Word so I can write on it. Notice at least there's one goblet that seems to be much higher than the rest for W1, W2, W4. Because I guess there's some discreteness here, it's hard to determine, does this line here continue to here, or does it go there, or does it go there? So that's why I circled those. So it looks like we have some particular goblet that's a little bit different from the rest. What you could do is go back to the original data set and try to figure that out using methods that we talked about in the graphics section. But what about trend with respect to the color that you see there? Notice how all the blues are higher than all the reds on W5. So what that tells me then is that, let's see, which variable? Oh yeah, well that is W5. Yes. So we would expect that because we made the division based upon the median. But what I wanted to say was look at W2 here. Almost all the blues are above almost all the reds. Well, what does W2 represent? The overall width. So there's something going on between that connection between the base and the cup and the overall width of the cup as well. Maybe it's intuitive to think of it that way because you're going to probably need a wider base to support a bigger cup. So maybe that makes sense to have something like that. Okay, so we did a little bit of an initial investigation. Now let's get back to the principal component analysis part. So to do the calculations that we need, we can use a function called prin_comp. Then we use an argument formula which tells R which variables we're going to use. So this works similar to what you would see for the LM function. But we have nothing on the left side of tilde. We have tilde. Here are my 5 remaining variables. Here's my Gallup data set. And then I also have an argument called core. So last time I told you there's actually 2 different ways to go about doing principal component analysis. One's based upon the covariance matrix. One's based upon the correlation matrix. The correlation matrix is much more frequently used, and you'll see why later. To introduce this, I chose to use the covariance matrix. So that's why I have core equal false there. To say use the covariance matrix. I'm going to put the results into an object called pca.cov to stand for covariance. And this is what I get. Okay. So when I simply type pca.cov at a command prompt, I get only a little bit of the information that's actually being done or calculated. Let me jump back over here to Word. So notice that we see standard deviation. Remember, the variance of y1 is equal to lambda 1. So what that means is that the estimated variance of y1 hat is equal to lambda 1 hat, which would be the largest eigenvalue from the estimated covariance matrix. The square root of a variance is a standard deviation. That's what that is there. So that's the square root of that estimated eigenvalue. This then would be then the square root of the estimated second eigenvalue. Now, whenever you encounter let's say an important function that does calculations in statistics, and you're using R, you might be thinking, okay, that's all that's being produced by this function, but there's a lot more. And so you should typically always follow the following steps of what I'm going to do next. A lot of you have seen this in other courses, but I know some of you probably have not. So the first thing that I would do is I want to check what exactly is returned to me from run and prin_comp. And so what I do is I'd say names pca.cov. What this function returns, as many R functions do when they do big calculations like this, is they return all the results into a list, just like what the LM function does. And we can see what's being calculated. So notice we have SDEV there. So to extract that, I can just say pca.cov $SDEV, and look what it is. It's exactly what was given to us before. But we also have some other stuff too. Okay? We will talk about those as we go along. Another thing that you should do then is find what is the class of pca.cov. Remember, every object in R has a class to it. And it just so happens, what often happens is that the class corresponds to what the function's name is. It doesn't have to be that, but that's how people program in R often do it. So we see we have a class of prin_comp. So then you probably are thinking, okay, based upon how R works, that must mean that there are probably some method functions and generic functions that can be used with a class of prin_comp. How do we figure that out? We say methods class equal prin_comp. And this is what we get. So what this is listening to us or listing for us are the generic functions that can be used with an object of class printcom. So the first one that I always would typically do when I see that function name there is summary. And so that means I can do summary, summary pca.cov. And now I have a summary of the information that's actually stored inside of pca.cov. And we see some of the information that we've already seen before. Hold on. Notice how we have that square root, the estimated variance. It's labeled as standard deviation. Notice we have proportion of variance. What this represents is actually, that's lambda hat 1. So the square, yeah. Is that right? Yeah. Yeah, I was going the wrong way. That was dumb. What am I doing wrong here? Hold on. Okay, it's proportion. Yeah. Okay, so let's see here. Okay, so there is the total variance, the total information that's being displayed. What did I do? I went back to the original data, found the estimated covariance matrix, and again, applying stuff from the matrix algebra section, I had to find the diagonal elements of that covariance matrix and then sum them. So that's my total variance. And there's the square root of that first eigenvalue. So if I find the actual eigenvalue itself, it's 0.09. So how about we take the ratio? 0.72. It's a little bit off there. I must be doing something. This is the problem sometimes doing stuff on the fly like this. It should be a 0.75. I'll look into it. Sorry about that. So what this tells me then is, let me come back over to R again. Come back up here. 75% of the variation in the data, 75% of the information that's available in my data is accounted for by just the first principal component. That is really good, really good. And if I wanted to, I could go up to the second principal component. And that will give me 14% more. So if I take, or should be able to take 0.13 squared divided by the total variance, I get 0.14. So what's the cumulative proportion? The cumulative proportion is 0.895. Typically, that should be good enough. And I should choose two principal components. That will be, I know 90% of the information in my data by only using two of these new variables. If I wanted to, I could also go up to 95% as well to get the 3. Now, if you notice in the actual notes, I use summary in a little bit of a different way. That's because there are some optional arguments that you can include. One of them is loadings. I don't know why, but loadings by default is false. Typically, we want to have it true. All that this is going to give you, or all this means, is show me those eigenvectors. Why do we use the word loadings there? Well, notice we basically have a linear combination that we're forming. Y1 is equal to A1 1 hat times x1 minus mu hat 1 plus, and you can keep on going down to the last one. Essentially, this A is loading x. It's forming the linear combination. And so the actual term that people use to describe them is loadings. So if you want to know what those eigenvectors are, you say loadings equal true. And what cutoff will do, let me actually show you what happens when I don't include it. Notice how you're missing this one right here. Sorry, I am getting ahead of myself. I apologize. In the comp 1 column, we have A11 hat, A12 hat, and so on. So in other words, this comp 1 is that eigenvector corresponding to the first eigenvalue. Comp 2 is the eigenvector corresponding to the second eigenvalue, and so on. Now, you might be wondering, why is that missing there? Well, let me show you what happens when I put it back in, that little argument. Notice how small that is. We'll get into this very shortly. By default, R will exclude the small ones. If you want to make sure that you include it, put cutoff equals 0. What that basically means is that if I look at, let's say, the absolute value of the values in the eigenvector, I want everything that's greater than or equal to 0. So by doing that, I get everything. Okay. Okay, let's go back in the notes. So this is on page 9. So those loadings, those A's, the coefficients on the linear combination are very, very important to us. So let's say we have a situation that looks like this. So let's say we just have 3 variables. And we have this for our first principal component equation. So it's based upon a linear combination of your x's. Notice that for x2 we have a 0 there. So is y1 representing anything about x2? No. We have a positive value, positive coefficient on x1. We have a negative coefficient on x3. So to interpret what this new variable represents, I would say simply it's a contrast between x1 and x3. These coefficients don't have to be exactly the same, but we can see it's one has a positive, one's a negative. So it's a contrast. It's comparing x1 to x3. And x2 plays no role at all. Now, I might have a situation like this too. x2 is playing no role, but x1 and x3 are playing a similar role. And so what we have here is that basically this is an overall measurement of x1 and x3. That's what this particular variable represents. I might have something like this. Now this y1 is representing a contrast again, comparing x1 and x3 to x2. So if I have large values of x1 and x3, no, I don't want to go there. It's simply a contrast. It's comparing the two. Imagine putting values of x1, x2, and x3 in there. What would happen? If you have large values of x1 or x3, if you have large values of x2, what would happen? It's a contrast between these two. Let's say we have something like this. What's y1 representing now? Just x1. Is this helpful to us at all? Not really. Why don't you just put x1 aside and work with the other variables? What this is saying is that x1 is already a distinct set of information different from all the rest. So ideally, we don't want something like this to happen. You can. You could imagine, let's say if I have a y2 that was had zero coefficients on x1 and x3. What happens if I have a y3 that has zero coefficients on x1 and x2 and something positive on x3? Well, what that's telling you is that you just have your original data set back. And you wouldn't want that. Principal component analysis isn't going to help you. So we will be very interested on what these particular values are. So let's go back to the example. Come on. Let me turn off my grammar check too. Okay. So this is A1 hat, A2 hat. And so what we're doing is we're going to be looking at these numbers here to interpret what does Y1 represent? What do you think? Is W6 playing much of a role? No. So what this means is an overall measurement of W1, W2, W4, and W5. Let's look back at the goblet. Remember, X3 is essentially a scaling factor, so let's ignore it. Look at X6 here. Remember, that was the one that had almost like a zero coefficient on it. So what the first principal component is basically measuring is essentially almost like the width of the goblet. It has nothing to do with height. That's how you would phrase your interpretation based upon what you see for these coefficients.
Can you repeat that phrasing part?
Okay. So what, I think I have it in, I should have it in the notes. Let me see if I can find it. There we go. Right there. It's a measure of the overall width of the goblet. Yeah. Sorry, I did jump around here. Let's look at the second principal component. This is the corresponding eigenvector that's forming the linear combination. Notice now we do have some negative values here. And so what we can see is that this is like a contrast between what W1 and W2 measure versus what W4, W5, and W6 measure. So let's go back to the plot. or the diagram. Let me do some erasing. Nope, that's not erasing. Look at, so we had negative values on W4, W5, W6, the base. It's all about the base, this particular variable, compared to the other parts, which generally for a goblet is going to be the top. The mouth, the X1, and X2 is the width of that. Normally you would see X2 is going to be, X2 is represented as the total width, but typically the cup part is always going to be wider than the bottom, so it's kind of like the top of the goblet, the width of the top of the goblet. Yeah, top versus base. And then we get to the third principal component. Again, it's a contrast, but now it's not necessarily clear what this is measuring. It's a contrast between W1, W4, and W6 versus W2 and W5. Perhaps you need to be an archaeologist to understand if that has meaning or not. Sorry, I can't give you a good interpretation. But this is how you approach principal component analysis. You're finding these eigenvalues, you're finding these eigenvectors. You decide how many principal components you want to use. We said 2. If you really wanted to, you could use a third one, but 2 typically would be fine. And then you try to interpret what those new variables, those principal components give you. Okay, let's see here. Now you might be wondering then, well, what are the actual numerical values for these new variables, these principal components? So you can actually calculate them. A common question that I will have on a test is calculate one of these for me. Either do all the calculations in R, or I'll say set up the actual equation to use to do the calculations. And you may or may not have to actually do the numerical part. So for, let's say, the first observation, what you would do is you find that first observation, those first observation values, subtract off the mean vector, pre-multiply it by, then, if we're talking about the first principal component, that eigenvector corresponding to the first eigenvalue, and that's how you get your y hat, the actual numerical value, out. So let's take a look at that. Just to show you that, or prove to you indeed, that this is for the first observation. So I take the first row of goblet. I'm going to copy that over to my Word document. Okay. And let me also copy over, there we go, these loadings. Okay. So I want to find y hat 1 for that very first observation. So what I would do is I take 0.7518 times W1, which would be 0.56, subtract off, and I have in my program how to find the estimated mean for that W1. The estimated mean is 0.7079. Then I keep on going down to the very last variable, corresponding value in the eigenvector, times the value of W6, subtract off its corresponding mean. How do I find those means? I guess I can show you what we've done before. I use the call means function, which says find the mean of each column. Here's 0.7. Here's 0.7, where you see my mouse. Okay? That's how you find the actual numerical values. And it ends up being negative 0.1477. There's an easier way to do this. You don't want to have to do this by hand, you could say. Instead, remember when we were looking at, well, what's actually stored inside pca.cov? There's actually something called scores. Often in statistics, the word scores represents what the predicted values or estimated values would be. Sometimes you hear people in regression analysis call the, let's say, the actual y-hats corresponding to your data values, your observed data values, as being scores. It's more of an older term. And so if I do pca.cov $scores, how about we just do the head on it? The value that we just calculated was negative 0.1476. So it's represented in that comp.1 column, which stands for principal component number 1. It's row 1 because we're talking about the very first observation. And there's that negative 0.477 there. Here's the negative 0.477 here as well. Okay. Another way to do this is you can use the predict function in R, very much how you use the predict function in R for regression models. If you want to predict for a particular regression model. And so if I say predict pca.cov, we see we get exactly the same thing for that very first principal component, first observation. Okay? I even go through the process, you can see this on your own, of how you could use R to basically do the calculation by using the equation. So for the very first observation, notice how I take out that first column, which corresponds to the ID variable. I subtract off the corresponding mu hat vector. And then this pca.cov $loadings, what that's going to give you is this right here. Type it out on your own just to verify that indeed how everything is related. Okay. Let's see here. So let's look at some plots. So what I can do is get out all my principal component scores. In other words, all of my y hat ones, all of the y hat twos, and so on, and plot them. This is what I get. I'm going to put principal component number 1 there, principal component number 2 on my y-axis. I'll explain the plot shortly. It's just basically using stuff that we saw in the graphics section. And here's a plot to those principal component scores, where I've labeled every single point by observation number. Do you remember number 4 and number 5? in the stars plot. Let's actually go back. Remember how number 4 and number 5 stood out from the rest? Okay. Actually, let me do a split screen so I can easily go back and forth. Look at how 4 and 5 stick out now when I plot the principal component scores. You would hope that, what we were seeing was something unusual in the stars plot. You would hope that it would also pop out here when we're working with the principal components. And it does. We're not losing that information because the first 2 principal components basically take into account or account for 90% of the variation in the data. Let's look at 24 and 23. They were different from the rest, although we didn't point that out. Notice that they have a big red and big black area, so W1 and W2. I think that corresponds to the cup, the top of the goblet. Notice how they stick out compared to all the other ones of the goblets. And they do that as well when we plot the principal component scores, the estimated Y1s, the estimated Y2s. Look at 17 here. Look how close it is to 4 and 5. How does it relate in the stars plot? Well, look at. Remember I said those were very similar, but just maybe slightly smaller, all the variables? They're close to one another based upon these principal components. So we would probably expect 18 to be close as well. Let's see if that actually happens. Yeah, it does. Now, in that stars plot, we saw a number of stars that were kind of small. They're all over there. So what this plot is telling us is that maybe we could come up with some kind of classifications for these goblets. So let me do a little bit of erasing here. And this is a little bit subjective. We could put all these goblets together. We could definitely put all these together. Oops. We could put these together. What do we do about these? What do we do about that one? Should that go over here or should it go there? I don't know. That's okay. We're being a little bit informal. There are more formal methods to come up with these classifications. But what principal component allows us to do, much better than if we were to look at all 5 variables simultaneously, it allows us to look at now our data in 2 dimensions and make some of those judgments now. Okay? Now, how did I do this plot? At least in the notes, I left this off. It was in the, it is in the actual program itself. PAR stands for graphics parameter. PTY says plot type. S, that option says square. I want to do a square plot, meaning the y-axis and the x-axis in terms of how it's represented on the screen are just about the same size. The reason why I do that is because remember what these principal components are measuring. The variance of y1 has the largest, is lambda 1. The variance of y2 is lambda 2. We know lambda 1 will be greater than lambda 2. What that means then for us is if we plot everything on exactly the same scale, which I do, what that means for us then is the variability in the y-axis, what we normally think of as the x-axis, the variability in the x-axis should be more than the variability in the y-axis direction. Do we see that? Yeah, we do. And so by putting everything on exactly the same scale, that allows you to see that, to understand similarities or differences much more than if you just go with the defaults for how R is going to plot everything.
Can you say that again? Why
Sure.
the X direction is more should have more variability.
Yep. Yeah, let me do some erasing too. That's why. So also, I want to make sure that I'm starting the x-axis and ending the x-axis at the same spot as the x and the y-axis, so I can see everything on exactly the same scale. So to do that, I run some code like this. Common dot limits gets find the minimum of all the principal component scores for the first two variables. Find the maximum of those principal component scores for the first two variables. Let me actually come on over here to 10 to show you that. Let's see, where's my plot? There we go. So this score.core2, which I might not have went over very well, basically represents, let's actually show the whole thing. Here are all my principal component scores. So for example, negative 0.1476 that we saw before was y hat 1 for the very first observation. So if I look at just the first two columns, I get my y hats for principal component 1 and for principal component 2. To make sure my plot is on exactly the same scale, I need to find the minimum of all these numbers, and I need to find the maximum of all those numbers. And so that's what I do here. The minimum and the maximum. Okay. I'm going to combine together the minimum and the maximum into a vector. Put that in an object called common.limits. So that when I plot my principal component scores for the first principal component, all the y hat ones on my x-axis, here's all my y hat 2s, my x-axis limits are going to correspond to the minimum and the maximum that I just found. That's going to guarantee that I'm going to use exactly the same limits for the x-axis, and then I do exactly the same for the y-axis. So that when I plot this, this is what I get. I forgot to do the par part. And there's my plot. The x-axis and the y-axis start in the same spot, as does the, and they all, both axes end in the same spot too. Okay, we're running a little bit later than what I anticipated. What I want to show you now for the project, part A of number 2, you're not going to be able to do yet. On number 2B, what you're going to do is take the NFL Combine data and you're going to run print comp with it. And then from that, tell me how many principal components should one use. There can be more than one answer, more than one right answer, but you're going to look at, for example, the percentage of variation, or you can use the scree plot, which is a little bit later in the notes, to make that judgment too. Yes.
So is B not dependent on A? Like this,
No.
Like the second part doesn't matter.
No, because, let's see now. I'm sorry. It's been a long week. Long few weeks. Yeah, you're not going to be able to quite do this yet. I apologize. Because you will need to use the correlation matrix. Thank you for bringing that up. If you wanted to get started, just say core equal true in that print comp. It's the next set of stuff in the notes. And you could use it if you want to. Then, similar to what we just talked about, interpret the principal components. And then you're going to do some plotting. You're going to do some other stuff as well. Yeah. I thought that I had gotten to a point where this was directly you could do yet. You can, but you'll just have to use the correlation matrix instead. You might want to read ahead. I apologize. Okay. So, what's next in our class? I'll have office hours. I need to end at 2:30. The reason being is because I am on the UNL Graduate Council. We have monthly meetings on Thursdays, one Thursday a month at 2:30. This is what oversees the graduate programs on campus. On Tuesday, we will continue with this PCA, and I promise you we'll talk about how to use the correlation matrix. And looking further ahead, project number 1 is due Thursday, October 9th. Test number 2 is Thursday, October 23rd. One last thing before you go. As I've said before, I think in this class, October 10th is a big day for the Department of Statistics. Myself and Aaron Blankenship, we are leading the presentation that we're giving to the Academic Planning Committee to reverse the decision to eliminate the Department of Statistics. This has taken a lot of time to put together. I'm probably working 60 to 70 hours a week trying to get this going. Because of that, I might change how we normally conduct class here. You're not going to lose anything, but we might use a different format, what's called a blended or hybrid learning format, to do our class instead that week. I use this in most of my other classes. I just chose not to use it here this semester. And so I might, for this 1 week, transform our class to more of a blended learning environment. If I do that, I will post something to the discussion board on Canvas. So please make sure you are subscribed to it. You do get messages from that. Because basically what I'll say is I want you to watch some videos before we would have our normal class. Okay, I'm sorry that might end up happening. You're not going to lose anything. But we might have to do that to help me get more time so I can prepare for that presentation. So, okay, that's all for today.